Pedro, I think you're the boss, right?
Yes, very good. Thank you very much. Thank you. So we'll move to the last discussion of the day and the first black hole discussion of the conference. So let me just remind people. So Juan and Samir are totally in charge of the first 20 minutes. And the goal is in the last 30 minutes to have an informal discussion. And one thing I forgot to emphasize in the last meeting is that there is a Slack channel where 300 people are already there asking a few questions. So do join and ask more questions there after the discussion if we didn't have time. And use also the discussion to ask questions about related talks of the conference that we did not have time to. So Juan or Samir, I don't know who is going to go first, please.
Juan, you're muted.
You are muted, yeah.
Well, thanks to the organizers for organizing this wonderful conference. I will first make a few remarks, and then Samir will make few remarks also. So in the 70s, people derived the black hole entropy formula, and they suggested that black holes could be viewed as quantum systems when they are viewed from outside, and that there should be e to the area over 4 G Newton states. And also, in addition, it should evolve unitarily. In other words, we can replace the geometry by a quantum system for all questions that we can ask about the black hole as long as we are sitting outside. But the question is, what are these states? Now, there are some key results from string theory. And the first result was in the context of supersymmetric string theories, and in addition, supersymmetric black holes in those supersymmetric string theories. Those are black holes that are charged and are extremal black holes. And these black holes can be counted precisely using strings and D-branes. And this reproduces the area formula, and not only that, but corrections to the formula, as we just saw in Pandosaya's talk. And we also saw the talk by Murthy, where we see that this project continues, and we get more and more precise and completely precise formulas for the entropy of the state. However, all these computations involve starting from the black hole picture and then changing some coupling or the expectation value of some field to a regime where we can do a weak coupling calculation in terms of, for example, branes and strings. And we do the counting using this picture. And then we argue that because we are computing an index or a protected quantity, that number should be the same also in the strong coupling picture where we do have the black hole geometry. And there are many alternative limits and possible counting schemes. We could also represent the black hole as some oscillating branes or as some gas of gluons, as we saw in the last two talks. But the question is whether we can see these microstates directly at strong coupling and using the Lorentzian gravity description. So what are these microstates as states in the Lorentzian gravity description? So it's been a project of trying to construct BPS supersymmetric fastballs. So this would be large families of smooth horizonless gravity solutions. And the state of the art is some papers, a series of papers by these authors and many others. And they appear to reproduce a fraction less than 1 of the entropy. So you could view this as a half empty, half full glass, but it looks like there might be such solutions. But one question is how this ADS2 description, or the black hole description, which contains an ADS2 near horizon geometry, how is that geometry connected with other possible solutions? Is that an average? And in particular, a physical question is, what geometry do I see when I fall into a black hole? Now, there are also black holes with non-zero temperature, and from ADS-CFT, we can certainly consider these black holes, and we can view them as fluids or states in strongly interacting quantum systems. And when we can calculate the entropy and we find quantitative agreement, this agreement is usually based on the Cardy formula for ADF3 times CFT2 or some variation of this. There is one case where numerical computations were done in the case of the zero-brane quantum mechanics, so that's a sort of a different approach for this problem. Now, there is also a separate development, which is a better understanding of entropy formulas. As I said in the beginning, these pictures of black holes are based on the original Bekenstein-Hawking entropy for the black hole. But now we have better formulas that give us the von Neumann entropy of the black hole. These are developments that started from the Ruta-Kanagi formula and generalizations. And the main result is that they have shown that the von Neumann entropy of a black hole depends on the geometry of the interior, the geometry we have in the interior. So this would suggest that the microstate of a black hole is somehow encoded in its interior, at least up to the RT surface. So if we have a definite microstate, we expect that the RT surface should be trivial. And but there are some problems or maybe puzzles, which is that the number of possible interiors is apparently larger than the number of microstates. So this is this bag of gold discussion where we can have very large spaces behind the horizon. And the way this problem is addressed is through these ideas of state dependence and code subspaces and so on, which I don't have time to discuss. And also there is another problem, which is that these geometries, when you evolve them in time, they contain a singularity. And hopefully this is just a speculation, maybe these two problems cancel each other, that somehow the singularity might play some role in cutting down the number of microstates or in explaining some aspects of black holes. And I think this is an exciting possibility, because perhaps the proper understanding of microstates might teach us something about the singularity. But these last two sentences are just my own speculations. Recently also, there's been a lot of progress that I guess will be reviewed in other review talks, or in other review talks and discussions on the page curve and the long time behavior of black holes. And these recent results were obtained using wormholes, and these are just new topologies of space-time. And they give results that can be interpreted as averaging over coupling constants in the quantum system. And in this situation, one can wonder whether the microstates should be more properly understood in a many universe wave function. So we might need the wave function of many universes to properly understand the black hole microstates. And certainly this is a point of view that's been recently highlighted in papers, for example, of Maroff and Maxwell. Now, I would like to finish just presenting one example of a string theory solution. This is not really a black hole problem, but it's an example of a string theory background with some kind of known microstates, you could say. So it's a classical Euclidean solution with entropy, which goes like 1 over G Newton, where the states that give rise to this entropy are known. And this is the so-called self-gravitating string solution of Horowitz and Polchinskih. And the idea is we consider a highly excited string state that self-gravitates, and that's supposed to be equal to a certain, or is supposed to be related to a certain smooth solution of the Euclidean background. So we can think of the left-hand side as we can think of this as a kind of string star. So we have a highly excited thermal string, and which is described by some smooth Euclidean solution involving a winding condensate. So this solution involving the winding condensate is a solution to the Euclidean action, which contains gravity and also a winding mode. So we have a Euclidean time circle of length beta, and we have chi is a field corresponding to the winding mode on the Euclidean circle. And the solution is reasonable and can be approximated by this action, as long as we are very close to the Hagedorn temperature, slightly below the Hagedorn temperature. And in this case, the size of the solution is larger than the string scale. And this works very nicely in 4 dimensions. I have here some formulas on how the size and the mass of the state depend on the deviation, but these are not important for us. What I want to emphasize is that from this action, you can derive the free energy, and you can also in particular derive that the entropy formula, which takes this form. So it's again an entropy formula for this classical solution. It arises because the mass of the winding mode depends on beta. So in this case, we know what the microstates are. They are just simply these oscillating string solutions. Now, as an exercise, you can imagine generalizing this for the black hole case. I'm not saying that the black hole case will be given in terms of strings, though many people have said that. That might be a possibility, but the question is, well, this case is not exactly identical to the black hole case. The circle never shrinks and so on. There is no horizon, blah, blah, blah. But it's similar I think it's similar in spirit in the sense that we have a Euclidean solution similar to the black hole Euclidean solution, which gives us the entropy, but we would like to find what the Lorentzian microstates are. Okay, thank you.
Thanks a lot, Juan. And let's switch to Samir, and then we will. Yeah, so let's maybe all thank Juan while Samir shares his screen. Perfect. And you did exactly 10 minutes, so it was perfect.
Okay, so can you see the screen and the cursor also?
Yes.
Thank you.
Yeah. Please.
Okay, thank you for the invitation to speak at this wonderful conference. So I'll just summarize what how I think about black holes and what I think we have learned from string theory. So here is the black hole information paradox. You start with a star, you collapse it, it becomes a black hole that emits entangled pairs, which up to some small corrections, which could come from any quantum gravity effects, are entangled between the outside and the inside member. So here is a picture where you see entangled pairs coming out. And so the entanglement keeps rising with the number of emission steps, and that leads to a problem at the endpoint of evaporation. This is a very robust problem. So if somebody says they'll try to make small corrections to each pair, epsilon is small, you can't actually trade that against the fact that n is large and say that somehow you'll delicately encode all the entanglement and in the end you'll be okay. Even if you take into account these small corrections, the entropy of entanglement actually keeps growing. So if you put corrections of order epsilon, you can't really lower the graph by more than 2 epsilon. So in fact, what one learns from all this is that the page curve actually cannot come down if 2 things are true. If the horizon dynamics can be approximated in any way by semi-classical evolution, which means the horizon in any description looks like this room. And second, in the description, in the proof of this small correction theorem, one does assume that there are no long distance, non-local effects. And so I'll come to that in a minute. Okay, so what's the solution to the puzzle in that case? A lot of people have worked on this thing which we call the fuzzball paradigm. And there one just says that if you start with a bound state of strings and branes, at weak coupling, it might have size of Planck length or string length. At strong coupling, what do we get? So naively, you might think that it will still be a small core of Planck size at the center, but around it, you will develop a large horizon, which is basically like the vacuum here. But that's not what you find. If you try to estimate the size of this bound state, you find that the size of bound states in string theory grows with the number of branes in it and with the coupling. And in fact, the estimate of this size performed many years ago shows that it's of the same order as the black hole radius for that much mass and charges. So then this suggests that maybe you just never get a proper horizon in string theory, and therefore you never have a problem. Everything is like a star or a planet. And now after this initial estimate, many examples of string bound states have been constructed. And in each case, one finds that you get a fuzzball instead of a horizon. So here is my cartoon of what the fuzzball program has been doing. So initially so all the states of the, let's say the D1, D5, P bar, like the extremal, near extremal black hole can be written in terms of some 5 branes, which are in green here, some D1 branes, which are in red here, and momentum and anti-momentum modes, which are in blue. So these are all the states can be written in that form. You can do initially all the two-charge extremal states were made, and one found they were all fuzzballs, no horizons. And then slowly more and more of this graph was picked up. And so basically, it's a little bit like the picture we have for M theory. You first capture all its limits, which are essentially the string theories, and you can perturb around them. So here we have all these kind of states which have been explored. And then in the middle, of course, you can say it's very messy, so we can't make a generic black hole state. Of course, you wouldn't want to. But here, all these states actually radiate. So then the small correction theorem catches you and then tells you if these states in the middle are not fuzzballs, then you have to actually have one of these three things in your theory, either non-locality over long distances or remnants or a non-unitarity. So you are either forced into one of these three, but if you don't like those, which I don't, then in fact, whatever you're learning from these limiting cases will have to continue to the inside also. So I think with all the things that we know, it's hard to imagine, at least for me, that there is any alternative to the fuzzball paradigm in string theory that you simply get a fuzzball and we are done. So recently there has been a lot of interest in what I'll call the wormhole paradigm. And there the idea might be that you want to maintain some kind of a semi-classical horizon dynamics in some approximation, but then, well, to solve the information puzzle and get the page curve to come down, you might have non-local effects of various kinds. So I do not find myself in agreement with at least what I have understood of these ideas. And so in this context, let me just try to say one thing, and that is, let me just try to write down what is the constraint we get from the small correction theorem on any ideas of this kind that one might want to try. So let's consider a scenario that is very tempting, but where the page curve will not come down. So please look at these assumptions and just keep them in mind to see in what situation the small correction theorem will tell you the page curve does not come down. So let's assume that the exact description of the black hole is something very complicated. This is the exact string theory. You can put it into a computer, and we are not even assuming that it's anywhere close to the semi-classical description that Hawking had. Suppose string theory does something very messy in this region. We won't even ask what it is. All we assume is the dynamics here is unitary. We'll also assume that far from the hole, physics is normal. That is, once you go past some distance, 100 m or whatever you like, all the physics here is the nice normal local physics you can read off from some standard string theory text. So no big non-local effects. And now suppose you assume now that out of these complicated degrees of freedom, there is some way to extract semi-classical dynamics, which is described by, let's say, a scalar field phi satisfying box phi equal to 0. We're not even going to specify what this map is, but there is some map in which it sort of looks like a semi-classical approximation. So in that approximation, now you have no choice, but you will get the creation of entangled pairs as the slices stretch. But we'll be very generous with our assumptions. We'll first ask that this effective field description. I've always put the effective descriptions in red and the exact things in black. We'll always ask the effective field description. It only has to work for low energy modes, say wavelength longer than 1 Fermi, where we understand the physics, nothing near the Planck scale. We're not even saying anything about that. And this effective dynamics also doesn't have to be 100% accurate. It only has to work up to some correction. And we won't even ask this map works for all times. It just works over a space-time region around here, which can produce, let's say, a few pairs. If I don't even have that, then of course, there's no sense in saying I have a semi-classical description there. But after you produce a few pairs, you may need a new map to get to make a semi-classical approximation. So you might think that we have put in all the possible assumptions. And with that, now in the exact theory, suppose you put into a computer, there's some radiation, some mess is going out. And the semi-classical, there is some kind of an approximation. So I have both these things. And then the exact thing goes to infinity. And here, as we said, everything is normal. It becomes some gravitons. And this also becomes some gravitons because at infinity, we have assumed everything is just given by normal low energy string theory. But because this was an approximate map, these will agree, but they can have an order epsilon disagreement. So that's, we have allowed that. Okay, so with all that, which might seem like a reasonable description of the exact theory and then some semi-classical approximation, the entanglement graph in the exact theory will not come down. Okay, so that's the point. In the approximate semi-classical theory, of course, going up. That was Hawking's original calculation. But with the assumptions we have made here, in the exact theory, which let's say is string theory fed into a computer, the entanglement will actually keep rising. And that's the power of the small corrections theorem. So it leads us with two very sharply different possibilities. If we just take the fuzzball paradigm, then the whole thing is like a piece of coal and just radiate from its surface like a piece of coal. There's no semi-classical approximation for Hawking pairs to look for, and you're done. Okay. And so that's it. But then the difficult part, of course, to show that you can actually support structure at the horizon, which is what all these fuzzball constructions do. But suppose you actually want to keep a semi-classical approximation in some sense to emerge with all these limitations we put. Very simple, for a few pairs, you want to get a semi-classical approximation, then there must be something non-local going on between here and here. You can need a non-local identification of bits or non-local Hamiltonian terms or so on. Something has to be done because otherwise it won't work out. It's not just entanglement, you need some change to the exact theory. And I think that's just very important to understand. This is the last slide I have. So let me just put it up here. I think, so again, with the fuzzball paradigm, I think that's the right way to go. To me, it looks like the right way forwards. There are many, many exciting things to do. And really this picture that the black hole actual states really don't have a smooth horizon. They are these interesting structures we find in string theory. You can't make them without string theory. All that we have learned from all the contributions of string theory that all people have put in the last 30 years goes into constructing these guys. And in particular, lots of inputs from Juan's work in the mid-90s and later. So we now understand the string states. Every time you try to take them and see what they actually make at strong coupling, they seem to make something like this. And that seems to be the end of the information question, at least as far as I can see. And with this, there are very many exciting things to do. I mean, you get good agreements of emission rates. You can get an understanding of scrambling, energy gaps, 3-point functions, 4-point functions, some recent work on observational signatures. So many people are doing very many interesting things with these. My own interest has been in trying to see what all this might apply for cosmology. There seem to be some interesting things you can say about possible sources of energy for inflation and dark energy and so on. On the other hand, when I look at the wormhole paradigm, I find that I find all those things very interesting. So I've been reading all those papers with great interest over the last couple of years. But in each case, I find that every time one puts in this approximation, one ends up with some problem with the exact theory, which now for me would be string theory, which is something I'm not comfortable in reconciling myself to. Each of those approaches ends up in one of these problems. I mean, the simplest is that you may either end up with remnants in Baby universe and the page curve doesn't come down. Okay. Or if you want to bring it down, the need to have non-locality of Hamiltonian interactions. And again, I'm talking about the exact theory. The full exact theory will need interactions, non-local interactions all the way across to distance n cube. Or some of those papers have non-unitarity of evolution in the black hole interior in the exact theory. And again, that may not be manifest. So each time I've looked at one of these things, I get stuck a little bit with this because I'm not comfortable with the assumption that the full exact string theory will actually have these kinds of behaviors. So a little bit more details of how I ran into these troubles.
Samir, maybe it would be good to conclude so to move to the discussion. We are a bit over time.
Yeah, thank you. So some of these were in my talk on this forum called Quantum Gravity and all that. But again, people can also talk to me in person, and I'd be very happy to see if there's any way of getting out of this. Okay, so that's essentially all I wanted to say. The fuzzball paradigm to me seems to be the right way forward. It has the inputs of everything we have learned from string theory and giving us very many exciting things to do. While if we try to make semi-classical approximations for the Hawking radiation, we seem to get into trouble. On the other hand, there are probably very good ways of using the black hole interior if you focus on the dynamics of infalling modes with energy much bigger than the temperature. That's what we call fuzzball complementarity. And it's a story which I've been thinking about for the last several years, and I'm happy to talk to people about that. But again, it's important to notice that these modes, E much bigger than T, have nothing to do with the information paradox, which only involves E of the order of T. So for the information paradox, I think we shouldn't be looking for these anything to do with the pair creation modes or the standard black hole interior. I think for the modes which are relevant to the information paradox, this is the only picture. And I think there's a large amount of evidence that seems to support this picture. So that's what I would tend to believe in. Okay, thank you.
Thank you very much. Thanks, Samir. Let's thank Samir and Juan. Let's thank both for a very nice introduction. Let me just suggest two things. So one is raise your hand. We will call you. And of course, if Juan or Samir think there is a particular person that would fit nicely at a given point, just override me and call that person. And if what you are then going to discuss is related to what is being discussed, wave so that we keep stay within the same subject. The second thing I want to remind is that there are two other discussions. One is called the black hole information paradox, and another one is on averages. So if you have questions that are not clearly related to those two sessions, then it's perfect to start here. If you are not sure, you can ask here. But the questions that are clearly not about those other sessions, let them go first. So if you think your question is better for one of those other two, please hold for a few minutes at least, so that we make sure we have time for the other ones on black hole microstates. Okay, so I open the floor now, and maybe we can start. Having said that, with I don't know, Eva. Say.
Okay, you can tell me if this is on topic or not. I think it is. So I want to ask about this notion that the two problems are connected, the singularity problem and the problem of the bag of gold that Juan mentioned, in a context where we have some understanding of what's going on as we approach the singularity. So let's suppose we think about a system that starts out with a single universe, and we ask, does it evolve dynamically to one with multiple universes? And if so, what's the dynamics for that? Because you mentioned that as a scenario for what's going on. So if we look at, let's say, non-supersymmetric BTZ black holes in the regime of parameters where, as you approach the singularity, there's a circle inside that has anti-periodic boundary conditions, and it shrinks slowly, then we know that the dynamics associated with the singularity is the condensation of winding strings there. As you approach the singularity, those winding strings may condense in a spatially dependent manner, meaning the condensation sets in, in a inhomogeneous way. So at that level, there would be, in some sense, baby universes forming dynamically, but the whole thing is approaching the singularity. So I'm not sure if that could explain this picture that there are multiple universes that dynamically are, that evolve from a system with a single component. So either in that system or in any other you would like to discuss, is there a particular prediction of this scenario for dynamics that leads in real time to topology change? And would that make a prediction in particular for these winding string condensation dynamics?
I personally don't know the answer to the question, but I think it's an interesting question, how the two ideas are related.
Yasunari, yeah, please.
Yeah.
Hi. Yeah, because precisely about that point, if you form effective description of the interior for, say, very high energy mode and hard mode, like what Samir was saying, from the degrees of freedom of the black hole, which is e to the a, or its tiny portion of it, then that's a finite dimensional system. So it's obviously cannot be used to evolve, time evolve infinitely towards the future. So in that sense, the theory has to break down. So you should have a singularity. It's in that sense, is that kind of, it has to be connected to the finite number of degrees of freedom and the singularity, at least in that sense.
Daniel?
Yes, I'd just like to respond a little bit to Samir's presentation. So Samir, I agreed with almost everything that you said, except for the part where you said that massive non-locality on the scale of m cubed is radical or unacceptable. And so I would of course, I would have agreed with that, had I been around, 30, 40 years ago. But we already know that that's a true feature of ADS-CFT, right? We already know that the space-time in ADS-CFT is emergent. And so that degrees of freedom, for example, things like commutativity of radial separation in the bulk is only an approximate notion. It only holds in certain states, and only to some approximation. In general, it can be violated at order 1. And so I think once we, in ADS-CFT, right, it's certainly our best understood theory of quantum gravity. And I would say that it comes down strongly on the side of radical non-locality at the scale of distances that are of order m cubed. So I agree with you that if we view that as unacceptable, then we're going to we have the problem that you're saying. But I think that, everything we've learned, in the last 10, 15 years about the emergence of space-time, quantum error correction, entanglement, and so on, is kind of exactly giving us a language for talking about massive non-locality and the emergence of space-time. And we now have also this new tool of using these Euclidean replica methods, which somehow seem to fit together very nicely with this idea of the emergence of space-time from entanglement. So I would suggest that maybe we should view that up with that option maybe as the right one.
Can I just comment on that though? I think I'm glad you brought that issue up, because I think that is maybe at the core of a lot of thinking about this wormhole paradigm. But I think there may be a mistake at the following step. So if you look at ADS-CFT, everything that we see from there is actually because of Hamiltonian interactions. Like if you take the CFT, every point in the CFT is interacting with its neighbors. That's what generates the entanglement. And if you look at it from the bulk point of view, then the gravity at one point is interacting with the gravity at the other point. So everything is actually happening with Hamiltonians, and ADS-CFT is completely right. I think what I'm not comfortable with is the following. I take 100 D-branes here. I make a little black hole of size 1 meter. I take 100 D-branes 1,000,000 miles away, make a little black hole of a size 100 meters. Take a very simple black hole like the 2-charge Extremal, where we actually know all the states, we've constructed them. But we can entangle these two D-branes, right? These 100 D-branes can be entangled heavily with those. All I see is that when we make all the corresponding gravity states in the first 1 meter pit, and all the gravity states in the second 1 meter pit, which is 1,000,000 miles away, I simply get two balls of gravity entangled with each other, but no physical connection, no non-locality.
No, but somehow if we entangle them in just the right way, then they'd be, all the observables, and we're learning more every day, for example, like in Ying's talk yesterday, behave exactly as if that connection were really there. And moreover, if you think about, as I said, I think it's important to realize that this issue comes up already in the ADS vacuum. You don't need to hide things behind horizons. You just ask, how do you think about local bulk physics in the vicinity of the vacuum in ADS? How is that consistent with the fact that everything is really described by a boundary CFT, right? And it's something, I think it's just true that the radial direction is not an exact property of the dual CFT. It's not something that's true in all states, even approximately. It's something that's only true in certain situations. And the mathematics of that, it just is sort of very compelling. Exactly the same mathematics tells you that if you entangle your two set of D3 branes that are 1,000,000 miles away, there will indeed be a connection between them, right? I don't think this is just philosophy by now. By now there are many calculations that all point towards the self-consistency of this picture. There are toy models where you can solve things exactly of various kinds, tensor networks, the SYK model, etc. Right? So it's not like we're just waving our hands and saying massive non-locality and then giving up, right? We have the mathematics, a lot of the mathematics of that. We don't have all of it, right? But I would say we understand it much better now than we did, 10 years ago.
But Daniel, I have read a lot of those papers, and let me disagree for the following reason. When you see something in ADS, I see everything actually working because there's a Hamiltonian connection. When things are far apart, I think the mistake that is being made is that Hamiltonians lead to entanglement. That is obviously true.
I'm not sure. In gravity, the Hamiltonian is a boundary term, right? In gravity, the Hamiltonian is a boundary term, Samir. So I don't understand what you're saying.
So Hamiltonian, actually, the on-shell value of the Hamiltonian is given by the boundary. The actual evolution is not given by the value of the Hamiltonian, but by its variations, and that's not a boundary term.
No, so it's not even about the Hamiltonian, Samir. The degrees of freedom in the middle of the space are not independent from the degrees of freedom at the boundary. That's the statement of holography, right? It sounds crazy, but we've learned how it works in large part. So I don't want to monopolize this. Maybe Suvrata.
Maybe let me just jump in. I'm not. I think it's okay if I jump in, because since I'm clearly not an expert, maybe I can say it and be corrected. But my feeling is that this would fit maybe better in discussing more information related things, like in the black hole information session. And,
sure, sorry, I was just trying.
I think to discuss really microstates and so on. Maybe there are other aspects that could be covered, but I don't know.
Yeah, Leo.
Yeah, my question is, yes, sorry. Yeah. My question is rather broad. And it's related to this work that we have just discussed in ADS 5 and in higher dimensional ADS. Now we have this very precise counting of entropy. But I guess I'm just trying to see if this is a message I should take. But that's not the entropy that would be related to the black hole. There's some other computation in n equals 4 that one should do to get to that entropy. Is that the correct statement of your talk or your presentation today?
Well, the question, so you computed the entropy when you did the field theory side by going to weak coupling and computing this index and so on. So that's a computation at weak coupling. The black hole is a solution that exists and is described by gravity when the coupling is strong. And the question is, how do we see those microstates in that gravity picture? Or that's part of the question. Yeah, so if you assume the duality and you assume the weakly coupled YAML's description, then and the index proper, the fact that the number doesn't change, you definitely get that. And well, the computations you did in the bulk by counting the zero modes and the determinants and so on, that's a computation directly done at strong coupling that is computing the number of states. But it only tells us about the states in a statistical way. That doesn't give us an explicit presentation of the microstates. In the first slide, I put this slide that says that the central dogma. So dogma means an assumption. It's something that we think it's true, but we cannot derive. We have not derived it, and we have not derived it from the gravity point of view directly. Starting from gravity and seeing the microstates is something that hasn't been done. I mean, of course, through the techniques of string theory and supersymmetry, we have many approaches, and we know a lot. But a very direct gravity understanding of the microstates, I think, would be wonderful.
Thanks.
So, sorry if I can just jump in because it's connected to what Juan said, but then you can bump me down the list of people to speak just for a moment, which is, I've been hearing this controversy like we all have for now over a decade. And I want to ask both of you, Samir and Juan, the following. There's a sense in which the fuzzball proposal is obviously true. And it is the following. If I can use ADS-CFT, let's take a state which has enough energy and, if you like, charge, and view it, say, in the conformal field theory. Now, there are many such microstates with this energy and charge. And therefore, if you believe ADS-CFT, there should be many such states on the gravity side. Well, most of those states are not going to correspond to smooth geometries. And whether you call them fuzzball or not, therefore, they will have gravity duals which are highly curved objects. So in this sense, isn't it obviously clear that, if you try to correspond microstates with microstates, you're going to have for, every microstate in the boundary theory, some kind of a fuzzball or highly curved state in the bulk. Given that that's true, then isn't the question, as Juan was saying, why is it that a black hole, which is a smooth geometry, often is a good approximation, or in what sense does it emerge as a good approximation? I mean, is that a way to think about the question, or am I just thinking about it wrong? Sorry.
Well, exactly what each microstate looks like. Well, that's part of the question. What does a typical microstate look like? And I think we don't have an answer to this question. So there are some ideas.
Sorry. Will it even be a classical geometry? I mean,
well, I think there is some argument. Let me try just to make an argument that it will be some kind of classical geometry. So this is an argument based on tensor networks. That the idea is that there are some qualitative similarities between tensor networks and space-time. So let me assume that these similarities are exact, and we can think of, so then if you have a very complex state, a typical microstate will be a very complex state. So it might be represented by perhaps a very long tensor network. And that length of the tensor network implies that the interior would be very long. And so it will be perhaps a smooth geometry with a long interior, perhaps filled with very different kinds of particles. So that might be one picture. But we don't know. It might be a singular space, as you were saying. So we don't know the answer to what the typical microstate is.
Can I also respond to Sandeep's question? Yeah. So I think there are two mistakes that many people might have been making in the past when they were first looking at black holes in string theory. And so both those points actually go towards your question. The first is that the black hole information paradox is actually the following question. If your quantum gravity theory has just some structure at the Planck scale, how do you actually keep some structure at the horizon? So that's the actual paradox. The no-hair theorems keep telling you that the structure will all fall into the horizon. Just saying that you have some massive jiggling at the Planck scale doesn't support anything. So not actually realizing that structure won't stay there. People just have something in the back of their mind. I'll have some complicated mess, it will stay there, so I'm okay. The information paradox really is that if you have structure only at the Planck scale, no matter what structure that is, it's actually all going to fall in. So the paradox is to show how do you get around that? And what we actually find in string theory is that there are these structures which are not just something happening at the Planck scale, but when you have a large number of quanta n, the physics, instead of being at the Planck scale, jumps to something like n times the Planck scale, and you get these extended structures. Now, if you don't use every facet of string theory exactly correctly, like even if you make a mistake of a factor of 2 in the string coupling and its connection to the Newton's constant, the fuzzball just collapses or becomes singular or gets a closed time-like curve. So really all of string theory goes into that, and that's what is the resolution of the puzzle. But the other half of the problem is that then people also started wondering whether out of all this mess, locally we could have effective degrees of freedom that would behave like local semi-classical physics. And then the small correction theorem comes and tells you, no, you shouldn't be looking for that. That's not possible. So in fact, both these mistakes, I think, were being made. First, people were thinking, okay, it's easy to get that kind of blob, and all we have to see is how does it give you a semi-classical approximation? Actually, neither of those is true. Supporting that blob is the problem, and then that blob doesn't have the local semi-classical approximation that one intuitively was thinking about. So you can still get local semi-classical physics possibly extracted for this E much bigger than T in for what I was calling fuzzball complementarity. But I don't know if that is true. It's just something we can make a bit model for. It's something which is possible, but I don't know if that is true. But for the information paradox, it's, I think, the opposite of what you said. The whole difficulty is in showing how does the structure support itself. And as we were just learning from the kind of thing that Juan has been doing recently, there can be other solutions. The CFT stops describing in Juan's picture the interior of the black hole once too much stuff falls in, and on the CFT only captures a part of the ADS, and the deep interior of the black hole is actually captured by something far outside. So you could have other solutions. So ADS CFT itself doesn't give you a unique solution, but the fuzzball paradigm itself, in the sense of your question, is the most conservative answer. That every CFT state in the boundary is a mess in the bulk, or a fuzzball in the bulk. It doesn't have to be an even near classical, it can be very messy, but how the structure supports itself is the question. And the way it supports itself is because the compact dimensions are no longer trivially tensored with the non-compact dimensions. So those structures are not obvious if they don't exist if you don't have string theory. And some of the old work of Juan with this Juan Maldacena mouse paper goes back to showing how you get some of those structures. So it's all very much coming from string theory. And without that, one hasn't actually addressed the information puzzle.
Subrat?
Yeah, sorry, I just wanted to say a couple of things. First, I wanted to agree completely with Daniel Harlow that, I think this issue of what you're calling non-locality is actually the fact that the Hilbert space doesn't factorize. And it's something we do learn from ADS-CFT, but I think as we have shown in several papers over the past few years, it also follows just from an analysis of the constraints of gravity. So that's just a robust analysis which doesn't require any exotic assumptions. And I don't think there's been any mistake that's been found in that. One may not like it, but I think it's an aspect of gravity. But turning perhaps more to the issue of microstates, I think the real question is that one needs to address is, if one looks at correlators of the metric or of 2-point functions of the metric near the horizon, are these correlators the same as what one would get from a semi-classical geometry in a typical state, or if they're not? And if the fuzzball proposal is that these correlators are somehow different, in a typical state than a semi-classical geometry, then I think that just contradicts several principles of statistical mechanics, as we showed in this paper with Pushkar. The input that goes into that is that using the Euclidean theory, you can compute fluctuations about the semi-classical geometry. And so you can't really have a basis of solutions in which these values of correlators are very different from the mean value. So I think that's something which suggests that one will never be able to push this program through to get a large set of solutions which differ widely from the black hole and still represent all basis states or a substantial fraction of basis states.
So is that a question for me? Maybe I can just make a comment.
Maybe we can let other people speak because we.
Please, yeah.
Let's say, Andy, do you want to make a comment?
Yeah, I want to make a quick comment on what Sendip said and then ask a question. So I don't think there's an obvious sense in which any context in which there's obvious sense that the fuzzball is right, because the entropy formula says that there's one degree of freedom per Planck area. And, so there has to be structure on the Planck area. And I don't understand why we would expect where there's structure on the Planck scale where quantum fluctuations become strongly coupled, we should hope that it would be described classically. And indeed, that would seem kind of a bad thing, because it seems to me that if it were described classically, that a black hole would be like a classical computer. And it seems much more likely that a black hole is a quantum computer, because it has to do so many magic things, scrambling, and all the basic things that black holes do. So I don't see that there. I mean, it could be right, but I don't see why we should expect it. The expectation would be that we need the full quantum space of possibilities to describe a black hole.
Andy, I wasn't saying it has to be classical, but I hear you.
But if it's not classical, it's not a fuzz. I mean, quantum. I think the fuzzball proposal is that it's classical. Maybe I've understood.
No, so that's not the proposal. No, absolutely not. Those solutions are don't have to be classical.
But then you don't have any equations. We don't have quantum equations.
Well, you do, right? What you've done is you've actually captured all the possible limitations, sometimes limits, like even you put some of these states of the D1, D5P structure that you had made at weak coupling. Some of them have, let's say, one string sitting inside a cap. We can find the dual to that. That's the string using the PPA approximation. And then you find if you put a condensate of strings, it again turns back to something classical. So you have quantum wave functions.
You can't solve quantum gravity at the Planck scale and write down solutions. At least that doesn't seem.
So
that isn't what I've seen in your papers. I've seen classical equations that you solve.
No, absolutely. All the limits are when you put, what happens is in the CFT, if you put many quanta per mode in the CFT side, the solution becomes close to classical. So what we do is it's like a black body radiation. If you have one photon in a box, you can solve it. If you have many photons in the same mode, you get classical electromagnetic waves. You can write a laser beam kind of thing by classical electromagnetism. We do both these limits. When you have something like a generic state of the black body, it is of course messy, but having captured the two limits, then you ask in the middle, if both of those didn't have a horizon, then you say in the middle, you shouldn't have a horizon. But if suppose somebody said, no, the ones which are more messy do have a smooth horizon, then the small correction theorem tells you must have some non-locality, which is fine. If you still want that, you can have that. But because you've captured all the limits, I don't think there can be any solutions really, in my belief, which do have a smooth horizon. So the game is whether you can actually have a horizon or not. And having captured all these limits, I think there's no room left.
Okay, let me. Yeah, that could be. Let me ask my question. It's from a comment of Juan's, but Samir maybe also. So you made the statement that we might try to find the microstates in the interior of the black hole. And does that mean that they're not in the exterior? And also, I got the impression with all the recent work on the wormholes and so on, that actually the drift of things was that there was much more happening far outside the black hole than we thought. The old picture that was in my mind, which has been modified by this replica stuff, is that black hole entropy in any kind of strongly coupled picture was some kind of state squeezed up near the right. I didn't really know, but now it looks like things are going out to M or 2M or whatever. So how are you reconciling this? Is it in the interior and the exterior, or just in the interior? Or
well, they might be different dual pictures, but the reason I made this remark is because there is a concrete formula, which is the Ryuta-Kanagi formula, which tells us that when we have black holes in certain pure states, like a black hole produced by collapse and so on, or even near pure states, the entropy of these black holes, the von Neumann entropy, is computed by looking at the interior and what's going on in the interior. So in the past, we paid attention to the entropy formulas, let's say the Bekenstein formula, to formulate our ideas of black holes. So now, whatever idea we have about black holes, it should take into account these new entropy formulas. So if we are going to say that black holes stop at the horizon and we have some fastball, then we miss the possibility of explaining why a black hole that forms from collapse will have low entropy, for example. We will not have a formula that can compute it. At least that formula ceases to be valid. And so I think our thinking of my opinion is that we're thinking about black holes should incorporate the latest black hole entropy formulas we have at our disposal. And it is the same formulas that tell us that sometimes some black hole interiors, when they're entangled with radiation, they should be thought of as part of radiation. It's exactly the same formula.
There's a question by Mark van Hamston.
Oh, yeah, actually it was kind of a variation on Andy's question that he just asked, but maybe I'll put it to Samir. So it was, again, basically trying to understand what is the rule of solutions that, so as Juan mentioned, it seems like there may be possibly many pure state solutions that have smooth geometry behind horizons, this bag of gold kind of space-times. And I'm wondering, suppose, I don't know that we've established that there are a lot of these, but it seems possible that there could be many of these solutions, these kind of pure state solutions with horizons. And I'm wondering, how does that fit in with the fuzzball paradigm? It seems like, I think for me, that was something surprising after all the fuzzball discussions.
Yeah, maybe I could comment on that. No, that's an excellent question, because I do think a lot about the bag of golds problem. And it's a very serious problem, because if you can just make a bag of gold initial slice, no matter what its evolution, you might then say, that you have that many states, and that's more than the Bekenstein entropy. So in fact, if you look at my recent papers on the Vector hypothesis, I try to address exactly how that works out in the context of fuzzballs. So let me just give you a very rough, like one-line kind of answer, which is not 100% accurate in this form. The idea is that there are so many of these actual fuzzball states, which are all coming because the compact dimensions can be, can twist around the non-compact ones in non-trivially tensor ways, because you have all these other solutions available. When you look at the space of all these solutions, the simple bag of gold solution where you just take the slice to be thin, smooth and long, but the compact dimensions are still trivially tensored, that solution is completely destabilized. It's not a good eigenstate. If you try to make that slice, it's not an eigenstate. Localizing on the entire superspace of states, space of all 3 geometries or 10 geometries to 9 geometries to that form, actually gives you a state of high energy. So if you actually try to make the bag of gold slice, because of the other solutions available, the solution is actually not a solution which is close to being on-shell. So if you actually look at, the presence of all these other solutions don't allow you to actually make a state which stays inside the horizon as something which is close to on-shell eigenstate. And that's very important, because if you could make that state, if you could make even one state which is stable at least for order a few crossing times, and or maybe longer than the crossing time, and which has a smooth horizon, you could then use it to create entangled pairs, and you would be back in the information paradox. So it's very important that these kind of smooth horizon things are destabilized by the large number of fuzzball states. So the exponentially large Bekenstein entropy of the states, that comes in as being crucial. And then you find that the large entropy of these states give you a measure in the phase space, which is comparable to the classical action. So the whole thing actually cannot be close to a classical solution. What looks like a smooth solution is not a smooth solution, and that's how the puzzle gets resolved. I don't know if that rough thing helps, but we can talk about it offline.
Yeah, I'm not sure I understand what when you say that the thing is destabilized by the fuzzball solutions.
So the energy,
what does that mean?
It means that if you try to find the energy of the actual quantum state, which is localized with having a trivially tensored, which has no spread in the fuzzball direction. So, you're just trying to focus on configurations which are narrowly confined to the compact dimensions being trivially tensored. In the whole space of all possible gravity solutions, you localize your wave packet to something quite narrow. But it does want to spread out over there just to minimize its own energy. And the moment you realize that you're squeezing it in those directions, the amount of energy you are having to put in to squeeze yourself away from those directions, fuzzball directions where you don't want to go, makes the mass of the solution more than ever.
Okay.
Let me have a suggestion, sorry, that like we did in the previous discussion, I think we should start in 20 minutes sharp. So let's thank Samir and Juan, but we can continue informally for a few more minutes still. But let's thank Samir and Juan.